15, it says the integral, I'm not even going to write it with the parentheses, even though they did. It's going to be x to the second power, 1/2 that, plus 3x. Mr. Gottlieb, if you're thinking I'm missing something, just give me some time, we'll get there. Well, let's check your answers. You should be able to do these without the answers, right? You just checking them? Good. Perfect. That's why we're there. So this is a -3, which means this is a -2, and dividing by a -2, so that gives me over 2, and a -2 here. Yep. Thank you for the catch. So 27. 27. All right, so 27 looks like integral x squared plus x plus 1 dx over x to the 1/2 power, right? There's no plus down here, right? So I can distribute this to everything up there, can't I? If I do that, I'm going to do this into this. So subtract the exponents, right? I get x to the 1/2. Or 3 has to be easier for what we're going to deal with in just a moment, right? And then this one become x to the 1/2. And then what does this become? What is 1 times x to the -1/2? X to the -1/2, right? 1 times a is itself. The other way you could do it, by the way, is you could put this underneath them. You could write this as the integral of x squared over x to the 1/2 plus x over x to the 1/2 plus 1 over x to the 1/2, right? And maybe you'll see it better if you did that. Does that make sense? Either way, when I take my integral, I'm going to get x to the 5/2, 2/5 out in front, plus x to the 3/2 plus 2/3 out in front, plus x to the 1/2 with a 2 out in front. Okay? Is that okay for 27? All right. And then on 29, obviously you're going to have to what? Boil it. Boil it first. VT is equal to, this is what we got when we did the problem on the previous page, right? VT is equal to 9.8t plus 20. So our velocity is that, agreed? For a ball getting thrown up in the air. Mr. Roebuck, find its acceleration. -9.8, again, we take the derivative. That falls off. This becomes -9.8, agreed? And then as a point of trivia, I asked you what's acceleration of time equals 2. It's a little tricky, but what's acceleration of time equals 2? -9.8, because there's no t in the expression, so that's kind of a dumb question, but it also makes it hard because it's a dumb question. Good, Spark? Okay. Now, let's do the fake something completely different. Let's say I gave you an acceleration is negative 9.8. How do I get to velocity, sir? You're going to take the antiderivative. So you can raise its power by 1. So you can integrate. So you're going to raise its power by 1 and divide by the power I get. Agreed? But we just did something very weird. Because what just happened, sir? We lost the 20. We need the 20. Where did the 20 go? First of all, Mr. Cross, why did I lose a 20? Yeah. When I take a derivative, what happens to this constant at the end? Goes away. What is that constant at the end, by the way? So why is it? How much stuff do you have at the beginning, right? If I plug in 0, that's how much I have at the beginning. So think about it this way. Let's say I'm putting water in a tub. And I tell you how fast I'm putting water in a tub. Do you know how much water's in the tub? No. You need to know, first of all, how long I'm putting water in the tub. Then you tell me how much I put in the tub. That still doesn't answer the question. What else do I need to know? How much I started with. This represents how much I started with. And a rate can't tell me what I started with. So the problem is when I do the antiderivative, I need to go get the rate I started with. Okay? So whenever you do an integral, you're going to recognize you're missing a piece of data. And that piece of data we write as plus c. In some classes, we would write it as plus whatever this is, not. Both of those work fine. Okay? Now, that means that every single problem we did on the previous page is wrong. What? Yeah, wrong. Plus C, plus C, plus C, plus C, plus C, plus C. Now they're right. That make sense? Now, C almost always represents the initial condition. How much water have the tub at the beginning? A little bit trickier than that because sometimes it doesn't work. So you have to plug in whatever values you get. Okay? So let's start off with the next sheet. Here we go. Not the next sheet, on the back of the sheet. I want you to read the problem about the evergreen nursery, and then I want you to try to start attacking this problem. You're probably going to get stuck, but try it anyways. Try it anyways. The back 60, problem 63, the back of 69. Yes, sir.
It's not you guys. Do you smell the gas? It's a strong gas smell coming from somewhere. But it's not in this area.
Yes.
I would check the chemistry room. I don't smell like gas room. You smell like gas fumes?
If it's downstairs, I'm sorry, pretty bad.
Now I think I smell it.
Hey, you think you're smelling it? You've been here like 2 minutes.
Now I think I
I think
can
I'm gonna
see.
pass out.
I'm not feeling too good.
My head hurts.
Ah,
It's strong.
Inhale.
I think I'm gonna pass out, Resli.
Evergreen nursery usually sells a certain shrub after 6 years of growth and shaping. The growth rate during those years can be approximated as DHDT equals 1.5 T plus 5, where T is in years, H is height in centimeters. The shrubs are planted, that's bad, sorry, planted when they are 12 centimeters tall. Find the height after T years. Okay. So I take a look at this and go, all right, well, I need to know height. I have the derivative for height. I need to get to the height equation. How do I get to the height equation? Antiderivative. So I'm going to integrate. Raises power by 1. Divided by the power I get. Plus C. Okay. So now I got to figure out what the initial conditions are. I got to figure out what C is. So I need a time where I know what's going on. What time do I know what's going on? I reread through the problem. Is there any time when I know what the height of a shrub is? 6 years. What I want to know. When they're planted, they're 12 centimeters tall. So 0, they're 12, right? So I plug in. I say, well, they got to be 12 when I put in a 0. Whoops, put in a 0. So all this is a 0, right? So this just becomes C equals 12. And so my equation becomes, for my height, H equals 0.75 T squared plus 5T plus 12. And that almost always happens. Almost always that initial condition is just going to become, that C is going to become whatever you have at time equals 0. That make sense?
Do you like want us to Can we just do it?
The answer is 92% of the time that's going to work beautifully. And then I'm going to throw a curveball at you and you're going to bunt it. The problem is sometimes this equation doesn't give me 0. If it doesn't give me 0, I got to catch it and make sure that I change that out. Now, most things when we measure something, we say at time equals 0, it is in fact, the growth has not yet affected it, right? So most equations, this is going to become 0, so therefore you can absolutely get away with it. Okay? But the good way to do it is to actually plug in and find what it must be. Does that make sense? Just in case it's a weird problem. Got it? All right. All right, everybody try bacteria growth.